All right, welcome everyone. If you've ever found yourself staring at a graduate physics exam question, feeling that mix of excitement and just a little bit of terror, then you are in the right place. Today, we're not just going to solve problems, we're going to decode them. We're going to build a mental toolkit to see past all the complicated equations and find the simple, beautiful physics that's hiding inside. So let's dive in. So, here's our game plan for today. We're going to start with the most important tool you have, the right mindset. From there, we'll dive right into the wonderfully weird world of quantum mechanics, looking at how particles behave when we're not looking. Then we'll jump over to the grand scale of classical electrodynamics to see how these fundamental rules govern everything from planets to electrons. We'll wrap things up with thermodynamics, exploring the absolute limits of what an engine can do, before we tie it all together into really powerful strategy for your exams. So let's get started with section 1, a physicist's mindset. Seriously, before we write down a single equation, we have to talk about the approach. I'd argue this is the most important part of your entire preparation. Let's be real about these exams for a second, because it's the absolute key to cracking them. They are designed to be tough. The point isn't just to see if you can plug numbers into a formula. I mean, a calculator can do that. The real test, what the person grading your exam is actually looking for, is your thought process. Can you look at a really complex problem and see the simple physics at its core? Can you build a logical bridge from the question they give you all the way to the answer? That skill, right there, is what separates a student from a physicist. So, to give us a solid structure, we're going to use what I call the pitch method for every single problem we do today. First, P is for problem. We read it, we understand it. I is for identify. We break it down. What exactly do we need to find? What physical concepts are at play here? T is for theory. Now we bring in the big guns, the fundamental equations, the core principles, like the Schrödinger equation or conservation laws. C is for calculation. This is where we carefully, step by step, do the math. And finally, and this is so important, H is for hindsight. We look at our result and ask, what does this actually mean physically? This last step is what turns a simple answer into real, deep understanding. All right, let's put our new framework to the test. Section 2, quantum mechanics. We are jumping right into a total classic problem, figuring out what happens to a single free particle over time. It sounds kind of simple, but trust me, it gets to the very heart of what makes quantum mechanics so strange and so amazing. Okay, so here's our setup. We have a free particle, which just means it's floating around in space with zero forces acting on it. At the very beginning, at time t equals 0, we know its quantum state is described by this beautiful bell curve shape, a Gaussian. So our mission, should we choose to accept it, is threefold. First, we have to make sure our math is physically realistic by normalizing it. Second, we need to fast forward time and see what this particle's state looks like later. Specifically, what's the probability of finding it somewhere? And third, we're going to check if it obeys one of quantum mechanics' most famous rules, the Heisenberg uncertainty principle. Okay, so let's apply our framework. Let's identify what's really being asked here. This problem is basically telling the complete story of a quantum particle. We start with its initial state, then the question asks, where does it go? How does our ability to know its position change as time goes on? And does all this behavior actually follow the fundamental laws of quantum mechanics, like the uncertainty principle? It's really a comprehensive test of our understanding of quantum dynamics. Now for the theory. The engine that drives time forward in the quantum world is the Schrödinger equation. You can really think of it as the quantum version of F equals ma. It's the fundamental rulebook for how literally everything evolves. And for our particle, we get this huge simplification. Since it's free, its potential energy, V, is 0. That whole term just, poof, vanishes. And that makes our job a whole lot easier. The other critical piece of theory here is the statistical interpretation, which we can thank Max Born for. You see, the wave function, psi, itself isn't something you can directly observe. But if you take its magnitude and square it, modulus psi of xt squared, that has a profound physical meaning. It is the probability density. The area under this curve between 2 points tells you the probability of finding the particle right there in that region. This is the crucial bridge between the abstract math and the reality of an experiment. Okay, time for the calculation. First up, we normalize. This is just a basic reality check. The probability of finding the particle somewhere in the entire universe has to be 100% or 1. So we solve a standard Gaussian integral to find our constant a. Now for the really fun part, making time move forward. How do we do that? The trick is something called Fourier analysis.
We can think of our nice, localized Gaussian bump as being secretly built from a combination of many different, infinitely long waves, each with a specific momentum. And the magic here is that we know exactly how each of those simple waves evolve in time. So we let them all evolve, then we just add them back together. After a bit of calculus, what we find is that our wave function is still a Gaussian, but it's wider and flatter. The final step is to square it to see what that probability of finding our particle actually looks like.
And now for the uncertainty check. This means we need to measure the spread in the particle's possible positions and its possible momenta. To do that, we calculate what we call expectation values, which is just a fancy term for the average value you'd get if you measured the same system over and over again. Now, because our wave packet is perfectly centered, the average position and the average momentum are both 0. The interesting part is the average of the squares of the position and momentum. From those, we can find the standard deviation for each. That's our sigma x and sigma p. And what you find is pretty amazing. Sigma x, the uncertainty in its position, actually grows with time. The final step is to multiply them together and see if we obey nature's speed limit, the uncertainty principle. And this is our hindsight moment. What did all that math actually tell us? Our neat, tight little packet of probability at the start just spreads out. It gets wider and flatter over time. This is called wave packet spreading. But why? Well, remember how we built our particle from waves of different momenta? The waves with higher momentum travel faster than the ones with lower momenta, so the whole packet inevitably just disperses. This is a profound takeaway. In quantum mechanics, if you just leave a localized particle alone, it will not stay put. Your certainty about where it is literally melts away into probability. Excellent. Okay, now let's tackle a more advanced problem, one that combines quantum mechanics with electromagnetism. This one's going to test our ability to work with operators and vector potentials. Okay, so here's the problem. We've got a charged particle that's sitting in two different fields at the same time. There's a uniform magnetic field pointing straight up in the z direction, and there's a simple harmonic oscillator potential, like a spring, that only acts in that same z direction. The question is asking for the energy eigenvalues. That's our cue that we need to set up and solve the time-independent Schrödinger equation for this whole system. So for our theory, we need to know the rule for putting electromagnetism into quantum mechanics. You can't just use the standard energy operator. The rule is called minimal coupling, and it basically says whenever you see the momentum operator P, you have to replace it with P minus QA, where A is the magnetic vector potential. You also add a term for the electric potential energy. Now, in our problem, there's no electric field, so the electric potential is 0. But we definitely have a magnetic field, so we absolutely have to deal with that vector potential A. Now for the calculation. First step is to find a vector potential A whose curl gives us our B field. A very standard choice for a uniform B field in the Z direction is this symmetric gauge you see here. Next, we just plug this A and our harmonic potential V into that general Hamiltonian formula. And this brings us to the trickiest part, the part where a lot of people make mistakes, expanding the P minus QA squared term. This is a common trap. You cannot just treat P and A like they're numbers because they are operators, and their components don't necessarily commute with each other. You have to write it out as P minus QA dot P minus QA and be super careful with the order of everything. And here's where the magic happens. When you carefully grind through all that operator algebra, something really beautiful just emerges from the mess. You get a cross term that looks like x times p sub y minus y times p sub x. And if you've been practicing, a little light bulb should go off in your head. That is the definition of the z component of the angular momentum operator, LZ. And just like that, our complicated Hamiltonian now contains a simple, familiar term that couples the magnetic field directly to the particle's angular momentum. This is a classic example of a deep physical connection just revealing itself through the math. So, for our hindsight, what did we learn here? The final form of the Hamiltonian, after all that work, is just beautiful. It completely separates. The motion in the z direction is just a standard 1D simple harmonic oscillator, totally unaffected by the magnetic field. The motion in the xy plane looks like a 2D harmonic oscillator, but with a frequency that depends on the B field, plus that term involving LZ. This means the energy eigenvalues are just going to be the sum of the energies from these two independent systems. And that energy is going to depend on the magnetic quantum number m bar, which is the eigenvalue of LZ. The huge takeaway is to respect the operator algebra and always be on the lookout for familiar structures like conserved quantities to simplify your problem. Okay, let's switch gears. We're going to leave the quantum worlds and head back to the classical.
Section 4, Electrodynamics. We're going to analyze a problem that is the absolute bedrock of celestial mechanics and scattering theory, the Kepler problem.
So here's our next puzzle. Imagine a light particle, say an electron orbiting a heavy, fixed charge like a proton. The force between them is that classic inverse square law. Our job is to figure out every single possible path that electron could take and to prove that the shape of its orbit, whether it's a circle, an ellipse, or something else, depends only on its total energy. And it's worth pointing out, the math here is exactly the same as the problem of a planet orbiting the sun.
Now, before we start, a quick pro tip on tools. In classical electrodynamics, vector calculus is your absolute best friend. This slide here is like your cheat sheet for the gradient, divergence, and curl. For a problem with spherical symmetry like this one, knowing these expressions in spherical coordinates by heart is a superpower. It'll save you so much time and frustration on exam day.
Okay, for our theory step, the solution rests on three absolutely fundamental principles. First, the force law itself, Coulomb's law, which is an inverse square central force. Second, because this force is conservative, the total mechanical energy, kinetic plus potential, is conserved. It's a constant. It doesn't change. And third, because the force is always pointing towards the center, there's no torque on the particle, which means its angular momentum, L, is also conserved. These two conservation laws are the keys to solving the whole problem without having to directly integrate the equations of motion twice, which is a huge pain. And this brings us right to the main result. By solving the equation of motion using those conservation laws, you can derive the equation for the particle's path, r as a function of the angle theta. The shape of this path, which is always a conic section, is determined only by the total energy E. If the energy is negative, the particle is trapped in a bound elliptical orbit. If the energy is exactly zero, it follows a parabolic path, just barely escaping to infinity. And if the energy is positive, it has more than enough energy to escape and it follows an unbound hyperbolic trajectory. And for our hindsight, let's just take a moment to appreciate how powerful this result is. This single analysis covers planets orbiting the sun, comets swinging by, and even the Rutherford scattering experiment that discovered the atomic nucleus. It is a cornerstone of classical physics. It shows how identifying fundamental symmetries, in this case rotational symmetry leading to angular momentum conservation and time invariance leading to energy conservation, can reduce a really complex dynamics problem down to a simple geometric one.
All right, let's move to our final topic area. We've done quantum and we've done classical mechanics. Now we're going to tackle thermodynamics by analyzing the most important theoretical engine ever conceived, the Carnot engine. So the problem is pretty straightforward, but it's also incredibly profound. We need to describe the 4 stages of the Carnot cycle, and then, using only the principle of energy conservation, the first law, derive a formula for its efficiency. The whole setup is an engine operating between 2 big thermal reservoirs at different temperatures. To set the stage for our theory, we just need to remember what the first law of thermodynamics really is. I know it sounds complicated, but it's just the principle of conservation of energy applied to heat and work. It says the change in a system's internal energy is equal to the heat you add minus the work the system does. And here's the key for an engine cycle. Since the engine always returns to its starting point, the net change in its internal energy over a full cycle is 0. This makes the math incredibly clean. This is the classic picture of the Carnot cycle. You see it in every textbook. I want you to imagine a gas trapped in this cylinder with a movable piston. The whole process is this kind of 4-step dance. We're going to put it on a hot plate, then we'll wrap it in insulation, then we'll put it on an ice cube, and then we'll wrap it in insulation again, all while letting the gas expand and compress. Let's break down exactly what happens in each step. So let's walk through the calculation, or in this case, the process. The cycle has 4 stages. First, an isothermal expansion at the high temperature T2. The system does work and it absorbs heat Q2 to keep its temperature from dropping. Second, an adiabatic expansion. It's thermally insulated, so as it expands and does more work, its temperature drops down to T1. Third, an isothermal compression at the low temperature T1. Work is done on the gas and it has to expel heat Q1 to the cold reservoir to stay at that low temperature. Finally, an adiabatic compression brings the system right back to its starting state, with work being done on it to raise its temperature back to T2.
So how efficient is this engine anyway? Well, the definition of efficiency, eta, is universal. It's what you get out divided by what you put in. What we get out is the net work, L, done by the engine over one cycle. What we put in, our fuel, is the heat, Q2, that we had to pull from the expensive hot reservoir. So efficiency is simply work divided by heat in. Now we just apply the first law of thermodynamics. For a complete cycle, the change in internal energy is zero, right? That means the net work done, L, must equal the net heat absorbed. The net heat is just the heat taken in, Q2, minus the heat that gets expelled, Q1. So L equals Q2 minus Q1. Now we just substitute this into our efficiency formula, and we get that eta equals Q2 minus Q1 divided by Q2, which simplifies really nicely to 1 minus the ratio of Q1 over Q2. And notice, we did that just using the first law. Now for the hindsight, and this is the most profound part. While we derived efficiency in terms of heat, the second law of thermodynamics lets us show that for any reversible cycle, like Carnot's, the ratio of heats, Q1 over Q2, is equal to the ratio of the absolute temperatures, T1 over T2. This gives us the famous Carnot efficiency, eta equals 1 minus T1 over T2. And here is the punchline. This is the maximum possible efficiency for any heat engine operating between these two temperatures. It is a fundamental limit set by nature itself. It doesn't matter if your engine uses an ideal gas or steam or anything else. It can never, ever beat Carnot. Wow, we have covered a lot of ground, from quantum wave packets to classical orbits, all the way to thermodynamic engines. So in this last section, let's pull it all together, synthesize the key themes, and talk about some concrete strategies for exam day. You know, looking back at all the problems we just solved, a few universal principles just keep showing up. First, conservation laws are king. In the Kepler problem, energy and angular momentum conservation were everything. In the quantum problems, energy eigenstates are central. You should always be asking yourself, what is conserved here? Second, symmetry is your guide. That spherically symmetric potential led directly to angular momentum conservation. Symmetries simplify problems enormously. And third, use potentials. In both E&M and quantum mechanics, using scalar and vector potentials is almost always more elegant and more powerful than working directly with forces and fields. And beyond the deep physics, there are some practical skills for the exam room. Always, and I mean always, draw a picture first. It just helps you organize your thoughts. After a long calculation, check your units. It's a super fast, easy way to catch mistakes. Before you circle that final answer, check the limit in cases. Does your formula behave the way you expect when, say, a charge or a mass goes to zero? And finally, be neat. Use a structured method like our pitch framework. A grader is so much more likely to give you partial credit if they can actually understand your thought process. So we'll end with a final thought. We've talked about all these concepts as tools for solving exam problems, but of course, they are so much more than that. They are the fundamental rules of nature. So I'm going to leave you with a question to ponder. As you look at the world around you, from the orbits of planets to the way technology works to the processes of life itself, which of these grand principles, the unbreakable laws of conservation, the deep elegance of symmetry, or the inherent fuzziness of quantum uncertainty, do you see as the most profound architect of our reality? Thank you for joining this masterclass.